Welcome to Study Loop.
Yikes, don't you hate it when a question like 48 has letters up to O? Okay, let's try to get through this one fast. So we have methyl, methylene, methylene, and then this aldehyde. Great, and so it's asking us if we react this with multiple reagents, what are we going to get? First one we got hydroxide. So of course that's going to make this carbon nucleophilic. It's going to react with itself. So we can generate 1, 2, 3, 1, 2, 3. This product, right? Next we have OH minus and formaldehyde. So this formaldehyde is going to act as the electrophile. So we'll generate this compound. For C, first we're doing LTA and then reacting with this aldehyde. And then we have water. So of course, LDA is going to make our alpha carbon supernucleophilic. We're going to introduce our aldehyde, so we're actually going to end up with a very similar product, but now we still have that methyl group that's attached. Pretty sweet. Moving on to D. We are reacting with CH2, CO2, ET2. That is this 1,3-diester. So I'll go ahead and redraw our, yikes, starting material. Looks, my screen doesn't really work that well off of that side, so draw it a little bit closer. This is going to be our nucleophile again. We're going to knock off one of these. Oh, actually, I'm sorry. So if we were using sodium ethoxide and ethanol, this is going to be the much more acidic proton. So this carbon is definitely going to be the nucleophile to attack this one, which will end up with this product. If we have acid, we could cleave off this whole group, but we're only ending with ethanol, so this is our final product. E, we're going to react this with methyl lithium and then water. So that's our product. Great. F, we have sodium borohydride, methanol. So of course that gets us to our primary alcohol. G, we have hydrogen with palladium on carbon. This is also reductive conditions to get us to our primary alcohol. For H, we have our glycol with tosylic acid. So of course this acts as your protecting group. We'll generate this acetal. I, we have CH3, NH2, and mild acid, which is the pH around 4.5. So here we're going to have our amine condensation. Double bond to our nitrogen with our CH3 intact to generate our amine, also known as the Schiff base. In J, we have dimethyl. Amine. So you'll generate the iminium, but that's super unstable. So of course this tautomerizes to generate the ene amine. The ene portion stands for the alkene, of course, and then you have just your amine. Okay, how we're doing? We are on K. So we're using CrO3, H2SO4, superoxidizing conditions. This is going to take our aldehyde all the way up to carboxylic acid. Okay, let's look at L, Br2, and we have this carboxylic acid. For M, we have this ylide. For N, sodium cyanide and HCl. And for O, we have LTA, CH3, I. Pretty sweet. Okay, so if we have LTA, this is what our starting material is like. So, of course, after we deprotonate, we can attack the nucleophile, or sorry, we can attack with this nucleophile to this electrophilic methyl iodide. To generate this product. For H, we're actually forming our cyanohydrin. So that we have nucleophilic cyanide attacking our aldehyde and opening it up, and then HCl to protonate that alkoxide. Finally, with our Wittig reaction, we're losing triphenylphosphine oxide in this reaction and replacing it with another carbon. So we end up with this entirely carbon hydrogen or hydrocarbon only with no heteroatoms.